Hello, welcome to my talk on the flight dynamics of boomerangs, impact of drag force and drag torque. A quick overview of my career. I had about 25 years of experience in industry and wireless technology, and 16 years of that I spent at Qualcomm designing the latest transceivers that went into iPhones and Galaxies, and I have over 50 patents. And also I had my foot in the academia, teaching wireless communication circuits at the university and co-advising about 12 students and about 550 plus IEEE publications. And currently I'm an adjunct professor in the electrical and computer engineering department at the University of California at San Diego. I'm also a technical advisor to several wireless companies. My interests are boomerangs and history of mathematics, and this work comes out of my hobby of throwing boomerangs. A quick overview of the agenda. I'll give a quick introduction to the history and championships of boomerangs, go over the prior work on the aerodynamics of boomerangs, and describe the derivation for the drag force and drag torque using the blade element theory, and discuss the ultra-wideband position location technology to track the flight trajectory of the boomerangs, and compare our UWB measurements results with the simulations, and summarize the work and talk about future work. A brief history of boomerangs. They're non-returning boomerangs that are found all over the world in every continent: Egypt, Europe, India, Australia, many places, and they're primarily used for hunting. The returning boomerangs are only found in Australia, and they're primarily used as a toy, although there are some speculations that they could have been used to hunt birds. Boomerang competitions have become very popular over the last 10 to 20 years. There are various competitions like Aussie round, fast catch, long distance, and maximum time afloat. More details of the competitions can be found in the International Federation of Boomerang Association official rulebook. There are several world championship records that are established that can be found on Wikipedia. They are categorized by Aussie, round, endurance, fast catch, trick catch, consecutive catches, and MTA, long distance. There's various categories. And these are the records that are held over multiple years. For different competitions, different types of boomerangs are used, that like the traditional Aussie or a three-blader or the hook or the Space Ranger. The prime event for boomerang competitions is like the 100 meters dash. This particular event is called fast catch.
One, two, three, four, one.
As you can see, that this particular event requires a lot of athleticism, and one of the authors in the paper is Manuel Schultz, who still continues to hold the record for the fast catch event. Now, coming to the aerodynamics of boomerangs, John Wasberg has developed the blade element theory, applied this to boomerangs, and developed the lift, rolling moment, and pitching moment in various boomerang aerodynamics in his paper. And we followed closely his approach, and last year extended his work to include the airflow from the front of the blade and also from the back of the blade as the boomerang blade rotates. A snapshot comparison of the prior work on aerodynamics can be highlighted in the three publications from Hess, starting from Hess in the 1970s, where the estimate for lift is directly proportional to the non-dimensional rotational speed, square of that, and Wasberg's analysis shows that it is proportional to half plus square of x by 3, and our analysis, which includes the reversal of airflow and reversal of angle of attack, shows that the lift coefficient is directly proportional to the non-dimensional rotational speed. More information on these papers can be found in the references 6, 9, and 10. In this paper, We have actually extended the work from the prior work of 9 and 10 from John and our work by including the drag force, which invariably happens as the boomerang rotates through the air. There's a drag force introduced, and in addition to drag force, there's also a drag torque that gets generated. So both we have derived expressions using blade element theory for the basic drag coefficient and drag coefficient with angle of attack, and drag torque, and for both basic and angle of attack. These non-dimensional basic drag coefficients have been plotted against the non-dimensional rotational speed, and as expected, they would increase as the non-dimensional rotational speed increases. Now, coming to track the trajectory of the boomerangs, there are various methods to do that. Perhaps most familiar to the audience is the global positioning system that is well known. Unfortunately, its accuracy is rather poor. It basically has an accuracy of about 10 meters, and the update rate, which means how quickly it can track, is only a 1 hertz. That is basically 1 data point per second. The other technique that's also being considered was video imaging using 3 different cameras. It offers good accuracy, but requires some extensive object detection and also camera calibration. It's subject to weather conditions like exposure to light, underexposure, or winds. So it makes it a lot more difficult to actually do video imaging. The third approach is using ultra wideband wireless positioning technology. This offers centimeter level accuracy and fast update, and it's immune to light and weather conditions as far as the measurement is concerned. So these are being summarized in the table, and we chose to go with ultra wideband technology as we've seen the most promising approach. A quick overview of the ultra wideband positioning technology. This technology has been around for the last 20 years. It's basically licensed, it's basically goes from 3.1 gigahertz to 10.6 gigahertz, and the bandwidth is approximately 500 megahertz each channel. So there's 14 channels over which we can deploy ultra wideband technology. It's unlicensed. Because it's unlicensed, the output power that can be sent out is limited. The ultra wideband technology baseband pulse can be seen there. It's a very narrow pulse, and it's described by the root raised cosine function, R of t. This technology is becoming quite popular now, with the accurate position location being of great interest. Recently, in iPhone 11, this particular ultra wideband technology has been enabled for spatial awareness. And there's more features, I'm sure, that are going to be coming. The idea of the ultra wideband technology is that the tag initiates a transmit, and the tag in this case being the boomerang. The tag initiates a transmission, and after a certain time, the anchor receives it and waits a certain duration and sends a transmit pulse back. The tag receives this, and by calculating the total time it took for the pulse to go from the tag to anchor and from anchor back to the tag, we can determine the approximate time that takes for the light to travel from the tag to anchor and from anchor back to the tag. And we can convert that time into distance, because these electromagnetic pulses travel at the velocity of light. Consequently, we can determine how far the tag is from the anchor. Just like in GPS, where we use 3 to 4 satellites to determine the position, in this case, we would need multiple anchors, for example, 3 to 4 anchors, to determine the position, because from the measurements, we get the distance from the tag to each anchor. And you can see that looking at the intersection of the circles, you can determine the exact position of the tag relative to the anchors. Since we are throwing a boomerang that moves in the air, we would also need to make sure that the tracking happens as the boomerang flies and comes back. We therefore built a 16 anchor mesh that covers 50 meters by 50 meters. And by using this, we were able to track the boomerang over the entire region. And we also track it in X, Y, and also Z. The ultra-wideband transceiver that we used in this case is the Decawave DW1000. It's a very well-known product that has been around for several years, and it consists of a receiver and transmitter as shown here. We embedded this wireless transceiver into our Boomerang by actually placing it in there and including the battery. And we made sure that the weight of the tag does not exceed the wood that is taken out. And this includes the battery too. And we made sure after the tag is installed that everything is smoothened out so that the aerodynamics is not impacted significantly. We measured the two-dimensional trajectory of the radiorang, and as you can see, we can actually see the flight trajectory of the boomerang. We compared our measurement results with the simulation results, and we see that the overall shape matches reasonably with our measurements. We can also compare the position X and Y versus time, and also we measured the rotational speed versus time, and we had to resort to using video imaging for the angular speed because there was no way to determine the rotation speed at this time using ultra-wideband technology. So quick summary of our work is that we extended the prior work on using blade element theory by including the time average drag force and drag torque. We simulated the flight trajectory of the boomerang, included by combining the lift, rolling moment, pitching moment, drag force, and drag torque. We measured the flight trajectory of the boomerang using ultra-wideband technology with 16 anchors and 1 tag. And it used a wireless UWB system embedded into the radiorang. And we compared the measurements of the radiorang with the simulation results, and the general trends are similar. In future work, we hope to measure the rotation, precession, nutation, and compare them with simulation. Thank you for attending this talk.